class. You know your algebra, functions, graphs, linear equations, yada yada yada. All right. It may not be as exciting as, say, rock and roll, but you'll discover that as the formulas may change and the variables get more complex, there's always one constant: adventure.
The Standard Deviants present The Adventurous World of College Algebra, Part 2. In The Adventurous World of College Algebra, Part 1, fearless Idaho Bones and his sidekick Boise discovered the lost golden X of Algebra, only to watch it fall into the hands of his arch-nemesis, the evil Wienerkopf. In pursuit of the lost X, Bones consulted ancient mystics, convened with otherworldly beings, and survived the deadly bite of coiled plastic play toys. Now, in Part 2, Bones will confront quadratic equations, get new shoes, defy general polynomials, bake brownies, and challenge his arch-rival for control of the infinitely valuable variable, the golden X of Algebra. All before you can say, oncoming peril.
Hi, I'm Gabrielle Smith, and welcome to the Adventurous World of College Algebra, Part 2. Over the next 2 hours, we'll reveal to you more mysteries of this ancient and excruciating, yet exhilarating subject. Part 1 of College Algebra crammed your brain with tons of functions, graphs, terms, algebraic properties, and linear equations.
Linear equations are chicken feed with a milk chaser. We're gonna find what we're looking for. We gotta move on to the real hog slop.
Let's ride!
In the adventurous world of College Algebra Part 2, we will square your algebra knowledge with quadratic equations, roots, complex numbers, polynomials, and the different operations you can perform with all these mathematical marvels.
In Abstractio, where I come from, we can always review a lesson by just going over it again in our minds. You earthlings still use mechanical devices to pause or to review. But that's okay. Not every life form can have such advanced intelligence. Just remember, while you're watching College Algebra Part 2, you can always pause the tape, stop the tape, fast forward, or rewind the tape at any time.
Of course, to truly understand algebra, you must attend your classes, read your books, listen to your professors, and do your homework. So go to class.
Part 1. Introduction to Quadratic Equations. Hello, this is Mr. Quadratic Equation. Nice to meet you.
Let us now focus our scopes beyond linear equations into new territory, quadratic equations. You remember from before that the degree of a polynomial is the highest exponent that appears in the polynomial. A quadratic polynomial has a degree of 2. Here are a few quadratics for your consideration. X to the second, or x squared, 5x squared minus 2x plus 3, and 7 minus x squared are all quadratic polynomials.
Excuse me, Mr. Math Guy? Okay, I'm here with him right now. We have a question. If the degree is like 2, okay, then
Yes.
why do they call it a quadratic? I mean, I thought quad was like 4.
Yes, of course. That's a very good question. In this instance, quad comes from the same root as the word quadrilateral, which is a four-sided figure like a square.
Oh, square. You mean like you?
Yes.
Okay.
An x with an exponent of 2 is called x squared. Quadratic refers to the presence of a squared variable.
In linear equations, the only power of x that appears is the first power. X to the first equals x. So linear equations have only first-degree polynomials. We'll see that when you multiply two linear polynomials together, the result is usually a quadratic. This is actually how many quadratic equations come up in applications, so you better get used to it.
All right, before we chart a course into unknown quadratic regions in our search for x, let's briefly go over 2 items.
squares and square root notation, and binomial multiplication.
Section A. Squares and square roots.
Well, we know you know that a number squared is simply that number multiplied by itself. 2 squared, or 2 times 2, is 4. 9 squared is 9 times 9, 81.
Now the square root operation is the inverse of squaring. If we square 9, we get 81. Taking the square root of 81 reverses the process and gives you back 9. If you square 1.2, you get 1.44. Reversing the process, the square root of 1.44 gives you back 1.2.
What is the square root of 25? You have to imagine the squaring operation and work backward. Figure out what number squared results in 25. Since 5 squared is 25, the square root of 25 is 5. The square root of any number a is the number you multiply by itself to produce a. For a few lucky examples like 25 and 81, you can figure out the square root just by thinking about the problem. But unless your number is a perfect square, like 25 or 81, the most practical way to find a square root for most numbers will usually be with a calculator.
Unless, of course, you know how to use an abacus, as our ancient brethren did on the Mount, or a slide rule like me.
What is this guy talking about? Go!
Remember, when looking for the square root of a number, you may get up to 2 answers, one positive and one negative. A calculator is designed to give just one of 2 possibilities. It will always give the positive answer. So, when we talk about the square root of a number, the answer is never negative. You'll soon see why the concept of negative square roots is pretty important and sometimes confusing.
There are 2 ways to indicate a square root in an equation. Both of them mean the square root, the one that is positive. The first way uses this notation, which you've probably seen. It's called a radical sign.
Dude, man, the point is that it's radical, man.
Dude, like, you are so cliche.
The radical is a square root symbol you'll see the most, so learn to love it.
A square root can also be designated by the fractional exponent, 1/2. So, radical a and a to the 1/2 power are both valid ways to write the term the square root of a.
Now, let's look at the square root of 9, radical 9, or 9 to the 1/2 power. We know that 3 times itself equals 9, so 3 is the square root, right? But -3 times -3 also equals 9. That means the square root of 9 could be plus or minus 3. When looking for a square root of a number, you may get 2 answers, one positive and one negative. We indicate this by putting a plus or minus symbol in front of the radical, like so.
When we talk about the square root of a number, the answer is never negative. But there's this problem of 2 square roots of 9, 3 and -3. The same holds true for any number. Both 4 and -4 are square roots of 16 because squaring 4 gives 16 and squaring -4 also gives 16. Remember, the radical symbol always refers to the positive square root. You must use a negative sign in front of the radical to indicate the negative square root. And if you see a plus or minus sign, that means that both positive and negative square roots are in play.
Now, nobody but your professor or Stephen Hawking actually knows how to find a square root in his head. So, like we said before, for most numbers, the best way to find the square root is on a calculator. But it's a good idea to know the simple ones by heart. What makes a square root simple? The square root of 16 is simple because 16 is a perfect square of a whole number 4. 4 times 4 is 16. So the square root of 16 is 4. 5 times 5 is 25. So 25 is also a perfect square with a square root of 5. You get the idea?
There are only 11 perfect squares from 0 to 100. They are 0, 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. And they all have simple square roots. It's pretty easy, really, and it's Well, it's important to be able to recognize them. It'll save you a lot of anguish in the long run. Imagine, anytime you see a radical 49, you'll know immediately to simplify it to 7. I promise you, whole numbers are a lot easier to work with than radicals. So learn your square roots. You will never be sorry.
Complex pedantic theorem, theorem, blah, 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 blah. Yes.
Question, confusion, bewilderment, question.
Response. Theorem. Yes.
Combative response.
Oh, disgusted reply. Theorem. Yes.
My pen blew up.
Section B, multiplying binomials.
Just as a bicycle has 2 wheels and a biathlete has 2 sports, a binomial, you recall, has 2 terms. For instance, linear polynomials like 2x plus 3 are all binomials. Monomial, binomial, and trinomial are all more specific versions of the term polynomial. While polynomial simply means many terms, trinomial tells us how many. 3 terms.
When multiplying 2 binomial expressions together, we use a method called FOIL.
Aside from being a useful household item that guys like Bones love to chew, FOIL is also, in effect, a handy use of the commutative and distributive properties of algebra.
A clever acronym, FOIL stands for first, outside, inside, last, which is the way you want to multiply out the terms of 2 binomials. Wienerkraft may have the golden X, but I've got the FOIL method to find it.
Here is an example using the binomial 2x plus 1 quantity squared, or 2x plus 1 times 2x plus 1. Sorry, gotta go. Wait!
To find the product of 2x plus 1 squared, first write the expression out longhand in the form 2x plus 1 times 2x plus 1. Now use FOIL. Multiply the first 2 terms, then the outside terms, then the inside terms, and then the last terms. So, multiply the first terms, 2x and 2x, to get 4x squared. Then multiply the outside terms, 2x and 1, to get 2x. Then multiply the inside terms, 1 and 2x, to get 2x. Then multiply the last terms, 1 and 1, to get 1. Simplifying this, we get 4x squared plus 4x plus 1.
Foiled again.
This method for multiplying binomial expressions can be used for any 2 binomials and can be modified to help find the product of higher order polynomials. For instance, let's try the quantity 3x plus 4 times the quantity x cubed minus 2x squared.
Here again, FOIL. Multiply 3x by x cubed to get 3x to the 4th. Then multiply the outside terms for negative 6x cubed, the inside terms for 4x cubed, and the last terms for negative 8x squared. Simplify to 3x to the 4th minus 2x cubed minus 8x squared.
FOIL works for any 2 binomials. Just make sure that each pair of parentheses contains only 2 terms. It doesn't matter what form those terms take.
And now you must learn about quadratics.
Section C, more quadratics.
We already said that a quadratic equation is the product of 2 first-degree polynomial expressions. Using FOIL, you can see that multiplying 2 linear polynomials will always result in one term with an exponent of 2. That is, the answer is always a quadratic polynomial.
Top 3 FOIL-related things not to be doing before your algebra exam. Number 3, FOIL origami. Number 2, foiling your pets. And the number 1 FOIL-related thing not to be doing the night before your college algebra exam, playing with your FOIL.
For example, the quantity 3x minus 1 times the quantity x plus 2 equals 3x squared plus 6x plus negative x minus 2, which is 3x squared plus 5x minus 2. A quadratic can always be put into this basic quadratic form. The equation y equals 3x squared plus 5x minus 2 reveals the pattern for the standard form for a quadratic equation. Y equals ax squared plus bx plus c, where a stands for the x squared coefficient, b is the x coefficient, and c is the constant.
A whole search for wiener crumbs is getting so complex.
All right, listen up, Boise. This parchment tells us that the standard form for a quadratic formula is y equals ax squared plus bx plus c.
Very interesting.
All right, let's move on.
The standard form for a quadratic equation is similar to the standard form for a linear equation, y equals mx plus b. The letters m and b are the traditional symbols for the slope and y-intercept of a line, but any of the letters work just as well. Using b instead of m for the coefficient of x, and using c as the coefficient that has no x, the standard linear equation becomes y equals bx plus c. Comparing this with the standard quadratic equation, the resemblance is clear. A quadratic equation is like a linear equation, except that it has another term, an x squared.
Now listen, my little munchkins. Quadratics are square, meaning they are of the second degree.
Hey, who's the guy in the laser suit?
Recall that with a linear equation, the slope or rate of change is a constant represented by m. That means it's the same for any point on the graph, which is why the graph of a linear equation is a straight line.
In the adventurous world of College Algebra Part 1, we introduced Sue. It costs Sue $1 per minute to speak with her psychic. If we look at the graph showing Sue's phone bill as a function of the time she talks, at any point on the graph, each additional minute adds an additional dollar. The rate is always $1 per minute, and that is the slope of the line, 1.
But unlike with linear equations, the rate of change for quadratic equations is not constant. In the practical world, quadratic equations are often used to model situations where the rate of change itself changes, so the slope is different at different points on the graph. One such situation is modeling the position of a falling object accelerating due to gravity.
Let's look closely at one gravity example to help relay this idea of changing rates of change.
In our example, position can be measured on the y-axis in terms of how far the falling body, or Detroit bones, is above the ground. As usual, the x-axis is used to show time. The body starts out 100 feet above the ground. Scientists have found that the equation in this context for position and time is y equals 100 minus 16x squared. By choosing different values of x and using the equation to compute y, we can find points on the graph. At time x equals 0, y equals 100. That point on the graph indicates the starting point for the fall. At time x equals 1 second, the equation is y equals 100 minus 16, or 84, shown by the point 184. At time x equals 2 seconds, the equation is y equals 100 minus 16 times 2 squared, or 100 minus 64, which is 36. This gives us another point on the graph, 236.
Now, these 3 points do not appear on a straight line. From 0, 100 to 184, the object has fallen 16 feet in 1 second. So on the average, it fell 16 feet per second. That rate is the slope of the straight line joining the 2 points. Similarly, from 184 to 236, the object has fallen 48 feet in 1 second. On the average, the object fell 48 feet per second, which is the slope between the 2 points. Notice that the rate is not the same for both calculations. First, the object fell 16 feet per second, then it fell 48 feet per second. As expected, the falling object speeds up. The fact that it speeds up means that you will not always see the same slope between any 2 points on the graph. The rate or slope is itself changing over time.
We found a few points on the graph by using simple numbers for x, 0, 1, and 2. A better picture of the graph can be found by finding many points using the same approach, but with x's like 0.37, 1.29, 0.03, and so on. The resulting shape, as expected, is not a straight line. Between different pairs of points on the graph, there will be different slopes, or rates. Plotted all together, the points on the graph form a curve.
I had a tough landing, but I was okay.
Oh, boss, are you okay? You got a little dirty, huh?
How'd you get here so fast?
I took a cab. You're like a fop. You're crazy.
We were getting
Come
close
on.
to Wienercroft. We got a tip he would be near the y-intercept for the quadratic, and I knew that could be found at C.
Section D. Graphs of quadratics.
When graphed, a quadratic equation takes the form of a parabola. The graph for the falling object we just saw is part of a parabola. Famous parabolas include the St. Louis Gateway Arch, a cross-section of a satellite dish, a cascade of water, the frown on a clown, and the graph of the function f of x equals x squared.
There are some great graphing calculators to help you with graphs of quadratic equations. Now we'll give you some good examples and details about the graphs of quadratic equations.
The graph of a quadratic equation is a curve that starts in one direction, turns, and then heads in the opposite direction. The point where the graph turns and changes direction is called the vertex. A vertical line drawn through the vertex splits the parabola into two symmetric halves. That line is called the axis of symmetry. The values of the coefficients a, b, and c will dictate the exact form for the graph of y equals ax squared plus bx plus c.
For instance, the value for a has a direct effect on both the width and direction of the parabola. If the value for a is positive, or greater than 0, then the parabola opens upward and the vertex is at the bottom. If the value of a is less than 0, or negative, the parabola opens downward and the vertex is at the top.
Additionally, the closer the value for a is to 0, the wider the parabola grows. And as a gets further away from 0, the parabola gets more and more narrow.
Note that a cannot equal 0. If a were 0, then what we would have is a linear equation. Why? Because if a were 0, then a times x squared would also be 0, which means there would not be an x squared a term. So all you'd have left is bx plus c, which is just a linear expression.
Remember, in a linear equation, the value for b was the y-axis intercept. Well, conveniently, in a quadratic equation, the value for c is the y-axis intercept.
Look at what happens to a quadratic equation when x equals 0. Y equals a times 0 squared plus b times 0 plus c. So if x equals 0, y equals c. The graph of the equation crosses the y-axis at c. As a special case, when c equals 0, the graph of the equation crosses the y-axis at 0. For the equation y equals 3x squared minus 12x plus 2, the graph crosses the y-axis at 2, because c equals 2. Remember, the graph intercepts the y-axis at c.
The axis of symmetry is a handy little line that conveniently can be found in handy equation form. X equals negative b divided by 2a. Let's look at an axis of symmetry example. For the equation y equals 3x squared minus 12x plus 2, the axis of symmetry is given by the equation x equals negative b over 2a. So x equals negative 12, or positive 12, divided by 2 times 3, or 6. 12 divided by 6 equals 2. Remember that the axis of symmetry is a vertical line. X equals 2 tells us where this line crosses the x-axis.
Remember, too, that the vertex of the graph, either the highest or lowest point, is always on the axis of symmetry. To find the vertex, we need both the x and y values. We know the x is negative b over 2a because the vertex is on the axis of symmetry. So to find the y, we use the standard equation y equals ax squared plus bx plus c.
For the example y equals 3x squared minus 12x plus 2, we already found the axis of symmetry x equals 2. When you plug x equals 2 into the equation, you get y equals 3 times 2 squared minus 12 times 2 plus 2 equals negative 10. This gives the point 2, negative 10, which is the vertex of the parabola.
Well, we're at the vertex, but where's the golden X of Algebra?
It looks like we'll have to brave quadratic roots to find it.
Let's go. Come on.
Part 2. Quadratic roots and factors.
Just as with linear functions, the real roots of a quadratic function are where the graph of the function crosses the x-axis. That is, the points where y equals 0. Since we have already determined that the graph of a quadratic equation goes in one direction, then turns around and heads back in the direction it came from, the graph can cross the x-axis a maximum of 2 times. Quadratic functions may therefore have up to 2 real roots. However, there are cases where the graph of a quadratic simply touches the x-axis once, at its vertex. These quadratic equations have 1 real root. And then there are those cases where the graph of the quadratic equation does not touch the x-axis at any point. Ever!
These quadratic equations have no real roots. They wander rootless through the infinite algebraic wilderness. Forever!
Not true. Quadratic equations without real roots must have imaginary and complex roots. Those numbers are found here with me on Abstractia. Don't worry, you'll be here with us soon enough.
We must eliminate the Abstractiana. I don't think so. I think she's cute.
Section A. Factoring quadratic equations.
One way to find the real roots of an equation is to factor it. Hey, Bones, what's factoring?
Well, Boise, you remember back in the classroom. In factoring, you break it down into the product of 2 binomial factors, and then solve each binomial for x when y equals 0. Factoring a quadratic equation is not necessarily a simple process, and it can get quite complicated when coefficients are very large. In some cases, the roots cannot be expressed as fractions or finite decimals. In these cases, factoring is impractical. But factoring is often the most simple way to find the real roots of an equation. So let's see how it's done.
Take the equation x squared plus x minus 6. Our mission is to find the 2 first-degree binomial factors which, when multiplied together, yield this as a product. So, you're trying to find what 2 factors multiplied out give you x squared plus x minus 6.
This just in. Finding the factors can be a brutal trial and error process, and there are no shortcuts. And that's just the way it is. Hang in there.
Before starting, let's review how 2 factors are multiplied using the FOIL method.
Arkansas will not foil me this time.
Take a look at this example. 3x minus 4 times 2x plus 1 equals 6x squared minus 5x minus 4. Notice that the coefficient of x squared, that is the 6, comes from multiplying the x coefficients from the 2 factors in parentheses. These are the first parts in FOIL. Similarly, the final coefficient in the answer, -4, comes from the last parts of the factors, from the -4 and 1. This pattern will occur every time you use FOIL.
Factoring is the reverse process of FOIL. We start out knowing the answer in the form 6x squared minus 5x minus 4, and we want to find the two binomial factors that are in parentheses. The point to keep in mind is this. The two first coefficients have to multiply together to form 6, and the two last coefficients must multiply to give -4.
We want to factor x squared plus x minus 6. Following the pattern just discussed, the two first coefficients, when multiplied together, must equal the coefficient of x squared, that is 1. And the last two coefficients in the parentheses, when multiplied together, must equal -6. What are some possibilities? The first could be 1 and 1, or -1 and -1. Either choice, when multiplied together, equals 1. For the last, we can use -1 times 6 and -2 times 3. These can also be ordered differently, and the minus sign can be repositioned in various ways. Just using the 2 and 3, for example, we have 2 times -3, -2 times 3, 3 times -2, and -3 times 2. These different combinations are all possibilities for the last coefficients. Looking at both firsts and lasts, there are many possibilities. Here is one. Make the firsts 1 and 1, and make the lasts -1 and 6. The factors are then x minus 1 and x plus 6. Unfortunately, there is no guarantee that this choice is correct. How can you tell if it is? Multiply them using FOIL and see if you obtain the quadratic we started with. X squared plus x minus 6.
What do you get when you FOIL x minus 1 plus x plus 6? Well, you get x to the second plus 5x minus 6, and that's not what we're looking for.
Obviously, that wasn't the right answer.
Unfortunately, this is not quite what we were looking for, so the factors we tried were wrong. This is where the trial and error part of the process comes in. You have to try different combinations of the first and last coefficients and check using FOIL whether each combination works. Sometimes you get lucky and you make the correct guess on the first try. Sometimes none of the combinations will work. But generally, you will find that a combination does work, and with practice, you will become better at guessing which combinations to try.
Here's a handy tip for you in working out all of your factoring problems. If the C coefficient of the quadratic equation is positive, then the signs inside the factors will be the same, either both positive or both negative. If the C coefficient is negative, then the signs in the factors will be different, one positive and one negative. In other words, look at this sign right here. It's positive. So your factors either have two pluses or two minuses. Wait, now it's negative. So you know your factors will have a plus and a minus. That's the tip. Okay, we still need to find the right factors for x squared plus x minus 6. You can solve this problem with your knowledge of factoring. Just set up the basic framework. We know that the coefficients of the x's in the factors must be 1 and 1, because the x squared has a coefficient of 1. What else do we know? Well, the C coefficient of the polynomial is -6. So we know that one factor has to be x plus something and the other is x minus something. Finally, we know that the pair of numbers multiply to equal 6, which means basically that they're either 1 and 6 or 2 and 3. We just tried 1 and 6 one way, and our answer wasn't even close. We got 5x in the middle instead of x. So we know that's not right. But we can try them again the other way. So if you FOIL x minus 6 times x plus 1, you get x squared minus 5x minus 6. Wow, that's even further off. Now the signs aren't even right. Let's try the other possible pair, 3 and 2, or x minus 3 times x plus 2. That equals x squared minus x minus 6. Oof, close but no cigar. That middle minus sign is still wrong. Okay, x minus 2 and x plus 3 are our last option, and they multiply out to x squared plus x minus 6. Money! Yep, that's our baby. So, through trial and error, we have found the factors for x squared plus x minus 6. They are x minus 2 and x plus 3.
The man makes me try to solve for x. I rant and rage and flex my pecs.
Gregory Pex! Gregory Pex!
I am just a bourgeois variable. I walk the number line.
Like a tightrope!
I am one factor among many.
Thousands and billions!
I am the square root of my father's anger.
He was a mean machine!
Section B. Finding roots from factors. Once we find the factors, it is easy for us to determine the roots of the equation simply by setting each factor to 0. Setting x plus 3 to 0, we find that x equals negative 3. Similarly, if x minus 2, the other factor, is also equal to 0, then x equals 2. These two values, x equals 2 and x equals negative 3, both result in a final value of 0 when plugged into our equation. Therefore, the real roots of the quadratic function x squared plus x minus 6 are negative 3 and 2.
This trick always works. If x equals 3 is a root, then x minus 3 is a factor. If x equals negative 8 is a root, then x minus negative 8, which is the same as x plus 8, is a factor. If x equals 346.287 is a root, then x minus 346.287 is a factor. You see the pattern, so here's the rule. For any real number r, if x equals r is a root, then x minus r is a factor.
Through this rule, you can see how factors and roots are intimately linked, kind of like love and marriage, Mork and Mindy, Brick and Brack, and dancing.
Usually, you have to factor an equation in order to find the roots. Sometimes you'll have the roots and be able to use them to find the factors. We'll give an example of that later. The point is that in the rest of our examples, we'll find both the factors and the roots. You don't get one without the other.
Since factoring is one of those things you'll do all the time in algebra, we'll do some more examples so you'll really get the hang of it. How about the factors for x squared minus 7x plus 12? First, ask what are the possibilities for first coefficients, the ones that go next to the x. 1 and 1 would work, or negative 1 and negative 1 would work. Like before, we'll start with 1 and 1 because that's easiest. Now, what are the possibilities for lasts? We need to choose numbers that will multiply together, resulting in 12. Some obvious choices are 1 and 12, 2 and 6, 3 and 4.
Trying these out, the first combination would be x plus 1 times x plus 12. Does that give the desired result of x squared minus 7x plus 12?
Using FOIL, we find x plus 1 times x plus 12 equals x squared plus 13x plus 12. Now that's not what we want. Next try. X plus 2 times x plus 6 equals x squared plus 8x plus 12. Wrong again. What about x plus 3 times x plus 4 equals x squared plus 7x plus 12? Still no luck. But this is pretty close. Just the sign for 7x is wrong. The correct answer is x minus 3 times x minus 4 equals x squared minus 7x plus 12. Looking back at our guesses, we can see that using two positive numbers for our lasts cannot possibly give a negative number for the combination of inside and outside parts. It would have been better to try negative numbers.
Remember the tip from before. If the C coefficient is positive, the factors must either be both positive or, like you see here, both negative.
Practicing many factoring problems will lead you to a number of ideas like that and will help you make better choices for the combinations you try.
Using the factors we found, the equation x squared minus 7x plus 12 equals 0 can be rewritten x minus 3 times x minus 4 equals 0. The solutions are 3 and 4, which come from setting x minus 3 equal to 0 and x minus 4 equal to 0.
Here's one more example. X squared plus 5x plus 3. This time, there are not many choices for firsts or lasts. Possible firsts are 1 and 1, or -1 and -1. Possible lasts are 1 and 3, 3 and 1, -1 and -3, or -3 and -1. There are 8 different possible combinations of firsts and lasts, and none of them work. This is a problem for which factoring by trial and error doesn't work. There will be another method a little later on for solving the equation x squared plus 5x plus 3 equals 0.
Yes, there will be a new method we will get to, and it's called the quadratic formula.
As we said before, sometimes you know a root for a quadratic, like if you discover a root while plotting points on a graph. You can use any roots you know to help factor the equation.
Here's an example. For the function y equals 3x squared plus 2x minus 5, one root is x equals 1, and this goes with the factor x minus 1. This is using the reverse logic from before. Instead of factoring first, then using the factors to find roots, this time we found a root and used it to make up a factor.
Now, knowing that x minus 1 is a factor means there's a way to complete this equation. X minus 1 times what x plus what equals 3x squared plus 2x minus 5. Like before, the factoring problem can be approached through trial and error, looking at combinations for the firsts and the lasts. But this time, we already know one first and one last. That reduces the amount of work big time. Boom! In fact, since one first is already known to be 1, the other one will have to be 3 because 3 times 1 must equal 3. Since one last is already known to be -1, the other one will have to be 5. Checking by multiplying x minus 1 times 3x plus 5, we get 3x squared plus 2x minus 5, which is what we wanted. Looking for roots, we set each factor x minus 1 and 3x plus 5 equal to 0. The first factor gives us the root we already knew, 1. The other factor gives us 3x plus 5 equals 0, which leads to 3x equals -5, and so x equals -5/3. So for this problem, the roots are 1 and -5/3. Boom! Great job!
Section C, single root quadratics.
Now you listen to me. There are no shortcuts. No shortcuts. No shortcuts.
Well, kinda. For a slightly different root-finding example, let's look at a product we found already when we FOILed two first-order polynomials together. Y equals 4x squared plus 4x plus 1.
Remember, we found 4x squared plus 4x plus 1 by multiplying 2x plus 1 times itself. Let's find the real roots of this function. We set y to 0, since the graph of the equation will cross the x-axis when y equals 0. So we have 0 equals 2x plus 1 times 2x plus 1.
Like our other examples, in order for this equation to be true, at least one of the factors must equal 0. Anytime there are two factors, we can set either factor equal to 0 and solve for x. In this instance, the factors are the same. They are both 2x plus 1, which means there will be only one root for the equation, since solving for either factor will yield the same answer. So we set 2x plus 1 equal to 0 and simply solve for x. Isolating x on one side, we get 2x equals -1 or x equals -1 over 2. So our root is -1 over 2. In this case, the quadratic equation has only one root.
We said before that when there's just one real root, the graph of the equation will touch the x-axis in just one point, and that point is the vertex. That means the vertex is the same point as the x-intercept. Now, we know from before, when we looked at the axis of symmetry, that the x value for the vertex is given by x equals negative b divided by 2a. Remember that the vertex is the only point on the graph that sits on the axis of symmetry. Don't forget to look at your insert card for this and other fine algebraic formulas.
So, this gives us another way to find these special one-root situations. Compute x equals negative b over 2a and then substitute that x into the quadratic equation to find the y-coordinate of the vertex. If y comes out to be 0, then you know x equals negative b over 2a is a root. Remember, roots are on the x-axis, where y equals 0, so it's the only root of the equation.
We can apply this idea to the preceding example. Y equals 4x squared plus 4x plus 1. Here, a equals 4, b equals 4, and c equals 1. The vertex occurs at x equals negative b over 2a, or after simplifying, negative 1 over 2. So x equals negative 1/2. Then y equals 4 times negative 1/2 squared plus 4 times negative 1/2 plus 1, or y equals 1 minus 2 plus 1, which equals 0. Since y equals 0, this proves that x equals negative 1/2 is a root, and since it is also the x for the vertex, it is the only root.
This jives with what we saw earlier. When both factors are identical, then there is only one single root for the equation. Often there are patterns to these one-root examples of quadratic equations, and it will make your life a lot easier if you can learn to recognize them.
Keep on going.
Section D, 2 factoring shortcuts. Kinda.
Here's a pattern for you for binomial squares. In a trinomial version of each equation, if the c, or final constant, is a perfect square, and the a coefficient is 1, then take the square root of c and double it. If the square root of c times 2 equals the b coefficient of x, then you know it's a single root equation. For example, you can see that 9 is a perfect square. The square root of 9 is 3, and 3 times 2 is 6. So you know that equation has only one root.
Also, you would recognize 100 as a perfect square. Its square root, 10, doubles to 20. So x squared plus 20x plus 100 fits this same squaring pattern, and you know it has only one single root. This trinomial has the same pattern, x squared plus 10x plus 25. The final constant is a perfect square. It is 25. Take the square root of that amount, 5, and double it. The result is 10, which is the b coefficient. That tells us that x squared plus 10x plus 25 factors into 2 identical parts, and even tells us what the parts are. The constant term for each part is 5, what we squared to find 25. So x squared plus 10x plus 25 equals x plus 5 times x plus 5. The equation x squared plus 10x plus 25 equals 0 has just one root, x equals negative 5. There are many patterns that can help reveal special kinds of factors. The best way to discover these patterns is to do many factoring and foiling problems.
Here is one more handy pattern that will let you factor equations more easily if you can recognize it. When there is no x term, that is, no middle or b coefficient term, and when the other two coefficients are both perfect squares like 49 or 25, there's a simple pattern to the factors. Check out this example. X squared minus 49 equals x plus 7 times x minus 7. You can FOIL the check. X plus 7 times x minus 7 yields x squared plus 7x minus 7x minus 49. Notice how the 7x terms effectively cancel each other out, and how the final constant is always a negative perfect square.
In other examples, x squared minus 36 is x plus 6 times x minus 6. x squared minus 1 is x plus 1 times x minus 1. And 4x squared minus 9 equals 2x plus 3 times 2x minus 3. In each case, the two factors look the same, except that one has a plus sign and the other a minus sign between the terms. The first values are both equal to the square root of the coefficient of x squared. The last values are each the square root of the last constant. All you need to do is put a plus between them in one factor and a minus in the other.
Let's take the equation y equals 16x squared minus 100. If you had to factor this and find the roots, this pattern makes it easy. You want to find the roots or x-intercepts. Following the pattern, you can see that 16x squared and 100 are both perfect squares, with square roots of 4x and 10. So you first factor 16x squared minus 100 into 4x minus 10 and 4x plus 10. That makes the equation y equals 4x minus 10 times 4x plus 10. Now set y to 0 since we want to find the roots. 4x minus 10 times 4x plus 10 equals 0. Finally, set each factor equal to 0 and solve for x. The results are x equals 10 over 4 and x equals negative 10 over 4. Simplify to 5 over 2 and you're done.
Yes, you may discover other shortcuts as you practice factoring and foiling, of course, in class and in your assignments. Now remember, do not play with your foil too much, as if you do, it'll tear. The most important way to factor, though, is by trial and error, even if it's a kind of a pain. And if that kind of factoring doesn't work, well, then you can always resort to the quadratic formula.
Section E, the quadratic formula.
Oh, she's so cute. Are you feeding her milk?
Oh no, I use the quadratic formula. She doesn't like it much now, but I think that eventually it'll help her SAT scores.
As we said, it is not always practical or possible to factor an equation, but it is always possible to find the roots of a quadratic equation by the use of another method, the quadratic formula.
We were determined to stay on course behind Wienerkopf and the x, but we came to a problem we just couldn't solve. No matter how much we tried and erred, we couldn't factor it. We didn't know what route to take.
Remember, we found a formula for the root of a linear equation to be negative b divided by m. In the case of quadratic equations, the root finding formula is, well, somewhat more complicated. The quadratic formula is x equals negative b plus or minus the square root of the quantity b squared minus 4ac, all divided by 2a.
Yeah, it looks nasty, but don't stress. It's a cakewalk.
By plugging in the values of the coefficients for a, b, and c, you can always come up with the roots of the quadratic equation. Again, using this method of quadratic magic, you may find 2, 1, or 0 real roots.
Okay, now for the rest of the quadratic formula. Remember the equation we failed to factor before? It was x squared plus 5x plus 3. Well, now we can factor it. You can always use the quadratic formula to find roots of equations that you can't factor any other way.
Here's how to use the quadratic formula to find roots. In our equation, a equals 1, b equals 5, and c equals 3. Now, to make things a little easier, before we substitute all these into the quadratic formula, let's just compute the part inside the square root. b squared minus 4ac, which equals 5 squared, minus 4 times 1 times 3, which equals 25 minus 12, which equals 13.
Yeah, you know what I'm saying. Listen up. That's 13 under the square root.
Now the rest of the formula is now easier to manage. We have x equals -5 plus or minus radical 13 over 2. Of course, that is really two answers. Using the plus part of the plus or minus sign, it is -5 plus radical 13 over 2. And using the minus part, we get -5 minus radical 13 over 2.
Radical, dude!
These cannot be expressed exactly as a decimal or fractional form. If you want to, you can compute accurate decimal approximations with a calculator. If you do, remember to add or subtract radical 13 from -5 first, and then divide that result by 2. Rounding to 6 decimal places, we get x equals -4.302776 and x equals -0.697224. But normally, you can just leave the answers in radical form.
So the quadratic formula helps you solve those equations you just can't factor any other way.
Oh, and by the way, these roots can now be used to factor the original equation. As we saw, if you know a root, then x minus that root is a factor. In this case, we have as an approximation x squared plus 5x plus 3 equals x plus 4.302776 times x plus 0.697224. The only way to give an exact factorization is to leave the square root of 13 in a symbolic form in the answer. X minus -5 plus radical 13 over 2 times x minus -5 minus radical 13 over 2. You can see why factoring this equation by the trial and error methods used earlier is sort of impractical.
And now here's some information for the discriminating algebra student.
The discriminant is the name for the part of the quadratic equation under the square root. b squared minus 4ac.
In the example we just did, the discriminant was 13. The discriminant is so called because it lets us discriminate with some at-a-glance insight between quadratics with 0, 1, or 2 real roots. After you substitute the values of a, b, and c into the quadratic formula,
I've found the discriminant.
if the value of the discriminant is positive, then there are 2 real roots to the equation. If the value is 0, then there is 1 real root. And if the value of the discriminant is negative, then you know immediately that there are no real roots to the quadratic equation.
So remember, if the discriminant is positive, then the quadratic equation will have 2 real roots. If it is 0, then there is only 1 real root. And if the discriminant is a negative value, then there are no real roots. Much like me, I'm often considered a negative person, and I moved around a lot growing up, so I have no real roots.
These generalizations are possible because the quadratic formula takes the square root of the discriminant. A square root of any positive number, you'll remember, yields 2 answers, one positive and one negative. And the square root of 0 yields 1 answer, since the only number times itself that will equal 0 is 0.
Wait. If the square root of a positive number gives 2 real answers, and the square root of 0 gives 1 real answer, which is 0, then what do you get when you take the square root of a negative number?
Ah, yes, square roots of negative numbers. What is the square root of a negative number? Well, the problem we run into here is the inconvenient fact that no real number multiplied by itself will ever give you a negative number. Never, not ever. So, what can you do when your discriminant is negative and you have to take its square root? Well, let me formally introduce imaginary numbers.
Section F. Imaginary and complex numbers.
At last! I told you we'd see each other again. Welcome back to Abstractia. Get comfortable, because as long as you're dealing with imaginary numbers, you're in my domain, and I protect those who come here.
To represent imaginary numbers, mathematicians use the number or symbol I. I is defined as the square root of -1 or -1 to the 1/2 power. Another way of saying this is that I squared equals -1.
Remember, Earthlings, even though it's a letter, I is not a variable. Also, it's not a real number. It cannot be found anywhere on the number line. It exists only in the mathematical mind. But it is very useful to you all the same.
I can be used to make other numbers with negative squares.
For example, 3i squared equals 3i times 3i equals 9 times I squared equals -9. Similarly, 4i squared equals -16. 5i squared equals -25. You get the idea. And just as the equation I squared equals -1 can be expressed in the form I equals the square root of -1, the equation 3i squared equals -9 can be written 3i equals the square root of -9. Similarly, the square root of -16 equals 4i. The square root of -25 equals 5i. The square root of -36 equals 6i. The square root of... And you get the idea.
Don't forget, the most important thing to remember here is the square root of -1 equals I.
To take a slightly more complicated example, we can look for the square root of -20. Now, radical 20 equals radical 4 times radical 5. The radical 4 simplifies to 2, so the square root of 20 simplifies to 2 radical 5. Thanks to the imaginary number I, taking the square root of -20 is not that much more complicated. In this case, the factors of radical -20 are radical 4, radical 5, and radical -1, or I. Simplifying the radical 4 to 2 and the radical -1 to I, we come up with 2i radical 5. Or to put it another way, the quantity 2i radical 5 squared equals -20.
Heidi-ho, ladies and gentlemen, I'm Red Cardinal. Little reminder for you. Now, don't confuse the square root of a negative number with the negative square root of a positive number. I mean, remember that any positive real number has two potential square roots, one positive and one negative. This means that 16, could have square roots of plus or minus 4, and the negative square root of 16 is -4, but the square root of -16 is 4 times the imaginary square root of -1, or 4i.
And if you varmints want to get extra silly, consider this. There are also two square roots of -16. 4i and -4i. I.
Now that you have been initiated into the world of imaginary numbers, you can see how all numbers are of 3 basic types. Real numbers, which are the basic numbers you know and love so well, imaginary numbers, your new and abstract friends, and complex numbers, a deadly mutant hybrid. No, just a combination of real and imaginary.
For example, 3 plus 4i, 1/2 minus 2/3 I, and 0.7 plus 1.3i are all complex numbers. A purely real number, one with no I part, can be written in a complex form as follows. Write 7.2 in the form 7.2 plus 0i. Now, why write anything in a more complex form? Well, sometimes you might have to combine a real number with a complex number. Similarly, a purely imaginary number, one in the form 12i, can be put in the complex form 0 plus 12i. This shows that all 3 types, real, imaginary, and combinations, can all be part of the form a plus bi. Anything in that form is called complex. If b equals 0, a plus bi is a purely real complex number. If a equals 0, a plus bi is a purely imaginary complex number.
Roots of quadratic equations found using the quadratic formula may be real, imaginary, or a complex form that combines real and imaginary.
Section G, a practical example.
One of the most common applications of quadratic equations in the real world is finding the speed of falling objects. Here's an example.
There's a special equation that models the position of falling objects in relation to time. This equation is y equals -1/2 times g times x squared plus vx plus h. Now you'll probably find this confusing, so we've placed this along with some other handy equations on your insert card. First, let's define the variables and constants we're using. The constants in this equation are g, v, and h. The value g stands for the acceleration of gravity.
No matter where you are on the surface of the Earth, the acceleration of gravity is a constant at 9.8 meters, or the American equivalent, 32 feet per second squared. Gravity is 9.8 meters, or 32 feet per second squared. You can learn this the easy way from me, or the hard way like Idaho did.
The squared part happens this way. Speed is measured in meters per second. Acceleration tells how speed changes. If speed gets faster by 9.8 meters per second every second, then you get 9.8 meters per second per second. This constant will be the same in every equation like this for Earth's gravity. The value v stands for initial velocity. Initial velocity is the velocity of the object when its position is first measured. That is, when time, the x variable, still equals 0. Finally, h stands for the initial height. The initial height is the height of the object when its position is first measured. The dependent variable y stands for the height in relation to the independent variable x, the time that has passed.
For our example, Galileo Galilei stands on the edge of a 122.5 meter high cliff with a bowling ball. He drops it off the edge. How long will it take the bowling ball to hit the ground below? Using the function we know between the position of a falling object and time, y equals -1/2 times g times x squared plus vx plus h. We can now answer this question. First, we must identify the constants. The height we are dealing with is measured in meters, so the value for g we use is 9.8 meters per second squared. Galileo doesn't throw the bowling ball, he simply drops it. So the initial velocity, v, is 0 meters per second. And since the ball is dropped from a height of 122.5 meters, the initial height, or h, is 122.5 meters. Plugging these values into the equation, we get y equals -1/2 times g, 9.8, times x squared plus v, 0, times x plus h, 122.5. This simplifies to y equals -4.9x squared plus 122.5.
Now, the variable y represents the height of the ball in relation to time x. We want to know how long it'll take until the ball hits the ground, which is where the height y equals 0. So, we must find the time x when the height y is 0. To find x when y equals 0, wait a minute, that's a root! In effect, we want to find the roots of the quadratic equation. Y equals -4.9x squared plus 122.5. There are a couple of different ways we can do this, and one, as we just discussed, is by using the quadratic formula.
In this quadratic equation, the coefficients are a equals -4.9, b equals 0, and c equals 122.5. We can plug these values into the quadratic formula in order to find the roots of the equation. This will give us x equals -0 plus or minus the square root of the quantity 0 squared minus 4 times -4.9 times 122.5 all over 2 times -4.9, which equals x equals plus or minus the square root of the quantity -4 times -4.9 times 122.5 all over -9.8, which equals x equals plus or minus radical 2,401 over -9.8, which equals x equals plus or minus 49 divided by 9.8, which equals x equals plus or minus 5. The value of x cannot be negative because Galileo drops the ball at time x equals 0. So x equals -5 would mean 5 seconds before he drops the ball. It's illogical. So the bowling ball hits the ground 5 seconds after it's dropped.
We could give you about 16 more examples of how to translate practical and word problems into algebraic equations, but we've still got some ground to cover. The fact is, if you know how to find the roots of any quadratic equation, either by factoring, using the quadratic formula, or solving for x, then you can solve any quadratic word problem as long as you plug your numbers into the right places. Your professors can help you figure that part out. And if you're unclear on factoring, the quadratic formula, solving for x, or anything else about quadratics, just rewind this part of the video and watch it again.
Part 3. Polynomials.
The algebraic universe grows ever more vast and complicated, and the creatures and equations in it grow ever stranger. We have dealt with linear equations of the form y equals mx plus b, and quadratic equations of the form y equals ax squared plus bx plus c. Continuing our search for the most complex equation in the known universe, we now turn our attentions to another algebraic mutant beast, cousin to the quadratic equation, the polynomial.
Yes, that would be polynomials, from the Latin poly, meaning many, and of course nomial, meaning the word that comes after poly.
Section A. General polynomials.
It appears that the Louisiana Bones is hot on my trail. General polynomials! Sir! You must find this San Francisco Bones and exterminate him! Go! Schnell!
We already told you about polynomials, but in case you forgot, here's a rockin' flashback. These terms and expressions are all polynomials.
We have seen general forms for linear polynomials and quadratic polynomials. In a similar way, the standard form for a higher degree polynomial has monomial terms made up of coefficients and powers of x, ordered so that the powers of x are decreasing.
Some examples are -7x cubed plus 2x minus 1, x to the 5th minus 2x to the 4th plus 3x to the 3rd minus 5x squared plus 2x minus 1, and x to the 20th plus x to the 5th plus x to the 3rd. Now we won't give each coefficient a different letter like we did for linear and quadratic standard forms, but we will have some things to say about two special coefficients.
The coefficient of the highest power of x, which is assumed not to be 0, is called the leading coefficient. In our first example, the leading coefficient equals -7. That coefficient goes with x to the 3rd power, so this example has a degree of 3. Likewise, the last example is a degree 20 polynomial, and the leading coefficient is 1.
The other major coefficient is the last one in the expression, the one with no x in it. That is, the one with the ghost x to the 0 power. This is called the constant term or the constant coefficient. We've seen it before as the y-intercept. So, in our first example, the constant term equals -1. In the third example, there is no constant term present. So, we say the constant term is 0.
Section B. Multiplying polynomials.
You also know, because we said it before, polynomial equations can be multiplied together using a modified form of the FOIL method. FOIL basically uses the distributive and commutative properties to distribute the terms from one of the polynomials being multiplied to the other. Here's an example.
Let's multiply the two polynomials, x squared minus 3x plus 1 and 2x cubed plus 4x squared plus 7x. First, we'll multiply each term in the first expression by every term in the second expression. So we multiply x squared by 2x cubed, 4x squared, and 7x. Then do the same with -3x and 1. Multiplying out all factors eventually yields 2x to the fifth plus 4x to the fourth minus 6x to the fourth plus 7x cubed minus 12x cubed plus 2x cubed minus 7x squared plus 4x squared plus 7x. Simplifying and combining all terms of like degree, we finally get 2x to the fifth minus 2x to the fourth minus 3x to the third minus 3x squared plus 7x.
This is a lot of calculations, and you must be careful to carry through any negative signs and to simplify correctly, or else.
Polynomials can also be factored or divided. Just like with quadratic equations, the roots of a polynomial function can be found by finding its factors. Now, finding the factors of a polynomial can be a long, complicated, messy, ugly, disgusting, annoying process. But you're going to be asked to do it on your tests, so you better learn it.
Section C. Factoring polynomials.
One way to find factors of a polynomial is through a form of algebraic long division that looks suspiciously like the long division you learned as a kid, only harder. For an example, let's try to see if x minus 3 is a factor of x cubed minus 7x minus 6.
When dividing x minus 3 into x cubed minus 7x minus 6, first set up the problem like a long division problem from elementary school. That is, you're dividing x minus 3 into x cubed plus 0x squared minus 7x minus 6. Now the zero's in there because there's no second degree term. Now you must ask yourself, what times x gives you x cubed? Of course, it's x squared. So you write x squared as the part of the quotient and then multiply x minus 3 by x squared, which gives you x cubed minus 3x squared, which you subtract from x cubed plus 0x squared to get 3x squared. Bringing down the next term, negative 7x, you have 3x squared minus 7x. Now we begin again, dividing x minus 3 into 3x squared minus 7x. Just looking at the first terms, x goes into 3x squared 3x times. Now 3x is the next part of the answer. Multiply x minus 3 by 3x for a product of 3x squared minus 9x. Subtracting, you're left with 2x minus 6. Now we see that x minus 3 divides evenly into 2x minus 6, which equals 2 without a remainder. So the solution to the long division problem, x cubed minus 7x minus 6 divided by x minus 3, is x squared plus 3x plus 2.
Since x minus 3 divides into x cubed minus 7x minus 6 evenly without a remainder, then x minus 3 is a factor of x cubed minus 7x minus 6. The quotient, which is x squared plus 3x plus 2, is also a factor of x cubed minus 7x minus 6. We now know that x cubed minus 7x minus 6 equals x minus 3 times x squared plus 3x plus 2. The quadratic expression x squared plus 3x plus 2 can be factored into x plus 1 times x plus 2. So, x cubed minus 7x minus 6 equals x minus 3 times x plus 1 times x plus 2. Setting the factored form of the equation x cubed minus 7x minus 6 to 0, we get 0 equals x minus 3 times x plus 1 times x plus 2. Thus, either x minus 3 equals 0, or x plus 1 equals 0, or x plus 2 equals 0. Solving all of these equations for x, we get x equals 3, x equals negative 1, and x equals negative 2. The roots to x cubed minus 7x minus 6 are 3, negative 1, and negative 2.
Note that there are 3 roots for this third-degree equation. You remember that the quadratic equation or second-degree equation we looked at always had at most 2 roots. A fourth-degree equation would have 4 or fewer roots, and so on. The degree of a polynomial equation always limits the number of roots.
Let's summarize the long division process for a third-order polynomial. First, find the partial quotient of x squared by dividing x into the first term x cubed. Then multiply x squared by the divisor and subtract the product from the dividend. Repeat the process until you either clear it out or reach a remainder.
I see you're working for Wienerkopf.
I am partial to bratwurst. Bones, I challenge you to an algebraic fight.
I accept.
What is the square root of 49?
7.
Factor x squared minus 100.
The quantity x minus 10 times the quantity x plus 10.
What is perpendicular to a line with slope 4/9?
A line with the slope of negative 9/4.
What is the square root of 9x to the 4th plus 10x cubed minus 8x squared?
Section D. Properties of polynomial graphs.
While graphs of polynomial equations will obviously be different from one to the next, they will always fall into one of 2 general categories, which we will now demonstrate. Polynomials all have either even or odd degrees. If you look at the simplest expressions, linear expressions, which have a degree of 1, and quadratic expressions, which have a degree of 2, you will see the following basic differences.
Even degree polynomials will always resemble the shape of the quadratic parabola with which you are familiar. They will either look like a scoop or an arch, possibly with a few little wrinkles somewhere in the middle. And odd degree equations will always look, well, odd, either positively odd or negatively odd.
What, not clear? This'll help.
The degree of a polynomial equation will dictate the shape of the graph of a polynomial. Any polynomial equation with an even value for its degree, like x squared, x to the 4th, x to the 6th, x to the 8th, and so on, will have a graph like a quadratic equation, in that it will hook around and exit the graph in roughly the same direction that it entered from. Even degree polynomial equations will either look like a scoop or an arc.
Any polynomial equation with an odd value for its degree, x to the 1st power, x cubed, x to the 5th power, x to the 7th power, and so on, will have graphs similar to third degree or cubic equations in that they are curved. But they are also like first degree or linear equations in that they always exit the graph from the opposite direction that they entered from. So they will always be, well, swoosh-like.
The simplest polynomials, single monomials, such as x cubed, x to the 4th, x to the 5th, and so on, illustrate these ideas. And be sure to notice that the higher the degree is, the thinner and steeper the graph becomes. It is important to recognize that for large values of x, high powers of x are so much larger than the lower powers that only the highest power will have much effect on the graph. To demonstrate this, compare the terms 2x to the 4th and 50x squared. For x equals 100, the first term is 200 million, and the second term, 500,000. Now compared to 200 million, 500,000 is small potatoes. For even larger values of x, the effect is even more pronounced. The point is this: for large enough values of x, you can ignore all but the highest degree term of the polynomial with little impact on the value of y. That means that for really large values of x, the graph of a polynomial must behave like a graph of the form y equals ax to the n power. For example, if you want a general idea of what the graph of y equals 4x to the fifth minus 3x cubed plus 2x squared plus 7 will look like for large values of x, just look at the first term, y equals 4x to the fifth. Now, this is what 4x to the fifth minus 3x cubed plus 2x squared plus 7 actually looks like. Pretty close, eh? See what we mean?
Also, just like with quadratic equations, the values of the coefficients for the first and last terms of a polynomial equation will influence the shape of the graph of that polynomial. For example, let's look at the effects on the graph of positive and negative values of the leading coefficient.
Look at these examples with even exponents and positive coefficients. You can see what happens to the graphs when the coefficients are made negative. The graphs flip over.
Now let's look at some graphs of equations with odd exponents and positive leading coefficients. Again, see what happens when the coefficients are made negative. You can see the general patterns.
For even exponents, the graph will have a V shape if the coefficient is positive, and will be a flipped over V if the coefficient is negative. For odd degrees, the graph will run roughly from lower left to upper right if the coefficient is positive, and from upper left to lower right if the coefficient is negative. These describe the general behavior of any polynomial if you take large enough x or negatively large enough x.
Okay, these generalities about the first term of a polynomial apply to the general shape of the graph, especially the parts far away from the y-axis. But right at the y-axis, you can get other useful information. In fact, you can read the graph's y-intercept right off the end of the equation. The constant is the y-intercept for any polynomial, same as it was for any linear or quadratic. This is true because the y-intercept is the point on the graph where x equals 0. And when x equals 0, all the terms of the polynomial, which include an x, will be 0, because anything multiplied by 0 is 0, except for the final term, which has no x.
For example, if y equals 4x to the fourth plus 3x squared minus 6x plus 5, then for x equals 0, y equals 4 times 0, which is 0, plus 3 times 0, which is 0, minus 6 times 0, which is 0, plus 5. So, y just equals 5. So, you can see that whatever the last coefficient in the equation is, that's where the graph crosses the y-axis, no matter what the rest of the equation looks like. And if there is no constant, then the y-intercept is 0, and the curve goes through point 0, 0, the origin.
Well, I finally found you, Wiener Croft.
Well, Pierre del Fuego Bones, I see you have defeated general polynomials. Very resourceful, Ohio Bones.
It's time to obtain the golden X of Algebra.
Polynomials tend to wiggle around a little bit somewhere in the center of the graph, but they can't wiggle too much. The degree places a limit on the number of wiggles or time that the polynomial can cross the x-axis.
For example, a polynomial of third degree, that is, its highest exponent is 3, can cross the x-axis at most 3 times. This corresponds to the point made earlier that it can have at most 3 roots. In fact, the graph of a third-degree polynomial can cross any horizontal line no more than 3 times.
Similarly, for any polynomial, the degree indicates the maximum possible number of times the graph can cross any horizontal line. Not every polynomial wiggles to the full extent allowed by this law. The polynomial y equals x to the fifth crosses each horizontal line just once. But if you can draw a horizontal line across the graph that hits it 4 times, say, then you can be sure that polynomial has a degree of at least 4.
In the real world, higher degree polynomials are actually very important. No kidding! Some applications for them are in graphic design, where higher degree polynomials can be used to create aesthetically pleasing curves of a variety of shapes.
Polynomials are also used in designing aerodynamic shapes for aircraft bodies and wings, and automobile bodies. It is the ability of high-degree polynomials to bend smoothly in prescribed ways that makes them useful for describing the aerodynamic shapes.
Yes, das ist. Ich bin kalt. Ich bin Eisländer und spreche nicht gut Deutsch. Ja! Algebra!
Forgy! Whatever you do, don't look!
So, this concludes part 2 of the adventurous world of college algebra. Quadratic equations and polynomials have been conquered, and you should give yourself a big pat on the back.
All right,
Gabby. We made it.
Hey,
Nice
thanks,
work.
guys.
Cool. If you have any questions or some things still have you a little confused,
Hey, just watch the tape again.
or give us a call at Cerebellum. Our number is 1-800-VCR-REVIEW, and we'd love to hear from you anytime for any reason.
And check out our other video course reviews, like The Dangerous World of Pre-Calculus, to shock your system into more mind-expanding college knowledge.
Bye-bye.
Bye. See you again.
Peace.
You've done algebra students everywhere a great service.
Did you like the health club membership we threw into the deal?
The club membership is fine. Where's the X?
We have our top dudes studying it.
Who?
Top dudes.
You don't understand the power of the X.
Don't worry. It's in a very safe place.
Bastards.